We're going to start today with, let's do some questions. What do you guys think? You guys got some? All right. 1 second, let me pull up the book so I can drop the screen grab the question in here. But Jack, I'll go with you first. All right, what you got here, Jack?
The 5.1 over 25, I don't know why I didn't figure it out.
Did I assign 25 from 5.1? Oh, 24? Okay. That sounds more familiar. All right. It says, use definition 2 to find an expression for the area under the curve for x cubed from 0 to 1 as a limit. So for part A, they're asking us to find this because we know the area is the same thing as the integral. And if I use definition 2, that says that I can think about this as the limit of the sum of f of x sub I delta x. So I need to compute then delta x, which is b minus a, divided by the number of subdivisions, which is n. And I need xi, which is a plus I delta x. So a was 0 plus I times 1 over n. So that's just going to be I over n. So if I plug in xi into my f of x, which is x cubed, and I plug in 1 over n for delta x, I have this. So far, so good? Okay. I notice here that the n cubed and the n have nothing to do with the sum because the sum is only indexed for i's, so I can pull those out. But they do have to still be inside the limit. And then I have sum 1 to n I cubed. And this is something that we have a formula for. If I go to think back to my, this is probably where part A ends. Because in part B, they give you the formula. So all I'm going to do in part B is I'm going to drop in my formula for n cubed, or for I cubed, or the sum of I cubed. And then we're just going to evaluate this. So if I FOILed this out, what do I have? I have like n to the 4th plus 2n cubed plus n squared. Oops. All over 4, but I need to move some stuff around there because I, like a dum-dum, forgot my limit and everything. And then I still have that 1 over n to the 4th times that stuff. So now all I'm left to do is evaluate this limit. And if I want, I guess I could simplify this down a little bit and just call this n to the 4th plus 2n cubed plus n squared over 4n to the 4th. If I try to evaluate this limit as it's currently written, I'm going to get infinity over infinity. This is an indeterminate form. So you could use L'Hopital on this, or you could use one of the tricks that we developed way back in chapter 2. Either would be appropriate. If you did L'Hopital, you'd have to do it 4 times as opposed to just using this trick way back from chapter 2 where I only have to deal with it once. So that's going to give me 1 plus 2 over n plus 1 over n squared over 4. And when I do the limit now, those pieces go to 0. So I'm left with 1/4. Yeah, because you're getting 2 over infinity or 1 over infinity, which is just little over huge, which is 0. At least in calculus land, right? Cool. Feel okay on that? So again, very much kind of like what we did in section 5.2 as well. And very much the thing that we're going to put away in section 5.3 and create a better way of doing this. Yes. Yes. Just like we pretty quickly put away the limit as, or the derivative as the limit of h approaches 0 of f of x plus h minus f of x over h. Because that was a hassle. Other homework questions you guys want to deal with before we start 5.3? Sophia. 5.2, number 25. Sure. Okay. Let's take a look here real quick. I'm going to grab like the whole bunch of this so I have the directions as well. All right. So it says use the form of the okay. So we have this. So the first thing that I'm going to do is I'm going to distribute this integral across the subtraction. And since I noticed that that whole function is in parentheses with the dx multiplying the whole thing, I can apply the dx to both integrals. Feel okay with that? In the second integral, I have this coefficient of 3. So I can go ahead and pull that coefficient of 3 out front of the integral. Okay with that? Okay. And now we are going to convert these into limits of sums. So we have the limit as n goes to infinity, the sum from I equals 1 to n of f of x I dx minus 3 times the limit as n goes to infinity of the sum from I equals 1 to n of g of x I delta x. So in each of these two situations, I need to create a delta x. Well, that's fine because they're going to be the same delta x because our bounds of integration are the same for each part. And create an equation for xi, and that'll be the same, again, because our delta x is the same and our bounds for integration are the same. Feel okay so far, Sophia? Yeah. Okay. So let's go ahead and plug all this stuff in now. So the first one was x cubed. And the second one was x squared. Now I'm going to cheat here. Because we just did this, right? Is that okay? So the same work, the exact same work. So I'm doing that. Is that okay?
Yeah.
Okay. This one, I'm going to go ahead and pull out or simplify things. Oh, I forgot my sum here. Sorry about that. I'm going to pull the n's out of that sum. So I have 3 n's. Is that okay? And this piece is something I have a formula for. If I went back through the chapter, I have that as the sum of I squareds. That was a formula that would have been given to you. If I foiled this stuff out, oh boy, what did I forget here, Mr. Kulik? Yeah, I forgot my limit. I did the same thing back here, didn't I? Oops, get it all. There we go. Sorry about that, Sophia. If I FOIL things out in here, what am I going to get? I'm going to get 2n cubed plus 3n squared plus n. So if I distribute that 3 over n cubed through, I'm going to have 6n cubed plus 9n squared plus 3n over 6n cubed. I'm just doing that, right? Is that cool? Okay. I said I didn't draw it, but if you're busy writing and only half listening, which happens to me all the time. Yeah. So I'm going to do I'm going to notice I'm in that same indeterminate form. If I plug in the infinities, infinity over infinity. So I'll use the same trick I used on that previous problem. So I'll multiply the top and bottom by n cubed. So I'm going to get 6 plus 9 over n plus 3 over n squared over 6. And if I do my limit, these guys go to 0. So I have 1/4 minus 1. I should get negative 3/4. And I'd like to impress upon you, like, the amount of work we had to do this. You can do this in, like, 3 equal signs at the end of 5-3, maybe less, which is, yeah, thumb time, Mr. Kulik. That's going to make my life a lot easier than having to spend half a sheet of paper kind of doing one problem. Okay. That's what you needed though, Sophia?
Yeah.
Okay, no problem. All right, should we go and do this thing then? 5-3. I'm excited to make my life easier. All right. So 5-3 is titled The Fundamental Theorem of Calculus. As you might expect, it's kind of an important result. It sounds pretty important. So, bless you. And the idea here, what the fundamental theorem of calculus is going to do, it's going to create a link between the integral calculus that we've been doing and the derivative calculus that we did first semester. So we're going to put these two calculus operations together, and that's going to make our lives way, way easier. Okay? So we're going to start by defining this function here. So I'm going to define this function g of x, which is equal to the integral from a to x of some f of t dt. So notice that this is a function in terms of x, and the x is the upper bound on my integral. So what you might think about this as the area so far function. So in this picture below, I have a graph of f of t. And as x varies between a and b, the area under that curve is going to increase, right? My value for g of x is just going to represent the area from 0 to x. The area so far going from a to b. Everybody's okay with that? Now, in the case of the drawing here, g of x is an increasing function because the area is always getting bigger. Could it be not increasing everywhere? Sure. What would need to happen? What if my function f of t dipped below the x-axis at some point? Then the stuff over here is a negative area, so then the area starts shrinking at some point, right? So in this example, or this illustration, g of x is increasing, but it need not always be increasing. Does everybody feel okay with what this g of x is, this like integral function, this area so far function? Let's take a little time out here and just do an example working with this function g of x, just to make sure we really understand what's going on. And it gives us another opportunity to talk about other ways to do an integral other than strictly using calculus. So this picture here that I've drawn is our function f of t. Notice that when I've graphed f of t, I've done this in a grid, right? I did that for a reason. Here we're defining g of x then as that integral function, the integral from 0 to x of f of t dt. And we want g of 0, 1, 2, 3, 4, and 5. Well, g of 0 is really easy because I know the integral from a to a of f of x dx is 0. That's basically talking about building a rectangle with 0 width. Obviously, the area under such a rectangle would be 0. So here, obviously, that's 0 as well. Everybody's okay with that? To get g1 then, I'm looking for this area. Well, geometrically, this is a triangle whose base is 1 and whose height is 2. So if I just want the area there, I just did 1/2 base times height for a triangle. So the area under or from 0 to 1 is 1. So my value g of 1 is 1. We okay there? Jillian?
Can you explain, like, if you go back to that, how you would verbalize it with words, like how you would say that? G of 0 is the integral, is it from?
Yeah, so it'd be the integral from 0 to 0 of f of t dt, which is equivalent to talking about the area with a rectangle, or rectangles with 0 width, which is Yeah, and it's like it's not a rectangle anymore. It's just nothing. Okay. So if I want to do G2 or G of 2, that's going to be G1, my triangle, plus this rectangle. Everybody agree with that? So G of 2 is the integral from 0 to 2 of f of t dt, which I'm going to break into the integral from 0 to 1, and then the integral from 1 to 2. So that rectangle has base of 1 and a height of 2. So my value for G1 was 1. And the area of that rectangle is 2. So my value for G3 or G of 2 is just 3. 1 plus 2. The rectangle is here. That was our answer for G of 1. That's okay. Again, if you're not understanding what we're talking about, like, stop me and ask. It's always okay.
So we're basically breaking down the graph into these little sections.
Yeah, into these little geometric figures, because, well, the graph is nice because it's what did I do before plus the next little piece, right? Which is what I'm going to approach it here. So if I look at this next piece, I have this, which was my G of 2, which I knew was 3. And then I have plus this little piece. Do I have a geometric way to find that piece? No. Why not? The sides are curved. So what am I going to do instead? Just going to approximate. So one of these boxes is one square unit of area, correct? That looks like 0.9 of a box to me. That looks like a little less than half. Maybe I'll call that 0.4. So this integral is just 1.3, approximately. Close enough for us. Everybody happy with that? Okay. So that's my value for G of 3 then is 4.3. 3 from G2 and 1.3 from that new piece that we just extended on. Everybody happy with that? Anytime that you're given an integral that's on a grid like that, and they're just asking for an approximation, it comes down to basically you just counting squares. You know what I mean? Okay. Let's look at G of 4. So notice here, I have my G of 3 that I just did, and then I have this new piece, but that new piece is below the x-axis. So I know that I'm going to be getting a negative area. So G of 3, which was 4.3, we just did. And this new integral should be negative because it was below the x-axis. And we're going to do the same thing. We're just going to make an approximation. So it looks like 0.9 and 0.4 again to me. So call that negative 1.3. So G of 4 is 3. We'll call it 3.0 because we did some approximating to one decimal place now instead of just 3 exactly. But whatever. Does that still feel okay? All right. So again, we have our G of 4 that we just did, which was all this stuff. We have this piece that's negative because it's below the x-axis. We'll make another approximation. To me, again, it looks like negative 1.3 units. So I get 1.7 for G of 5. Does that feel okay there? So if you're given a graph and it's on a grid like that, you can geometric it out. or even if the graph is all straight lined, you can geometric it out, just break it up into rectangles and triangles and stuff, and just do it geometrically. There's nothing wrong with doing that. In fact, that's what they're hoping you're going to do if you're given a picture. So if I wanted to then graph g of x, so I'm going to plot the points like x comma g of x, and I get something that looks like this. Notice that we were increasing until we got to x equals 3. What happened at x equals 3? F of t dipped below the x-axis. So the areas we were getting after that point were negative. That's why the function reached g of x reached a maximum at 3, because after that point we started adding negative areas, so the area started decreasing. So again, this is like g of x, which is like an area, is our y-coordinate. Does that feel okay?
Sorry, can you say one more time why your max is at 3?
So if I go back and I look at my function f of t, at 3 is where the function dipped below the x-axis. So all the areas that I was calculating after that point were negative areas. So the area now starts decreasing, getting smaller because I'm adding negative areas in.
You just found, you don't know if it's specifically like that, it could be like that, or
Yeah, I'm just making an approximation. Yeah. So I just plotted like my points that I got, and then like fit a smooth curve to it. I don't know that it's going to be like, that it's not going to be like, like straight lined as opposed to curved. I don't know that. I just, made an approximation. Is that okay? So again, that's just my graph of g of x. Okay, here's the big question. Is there a relationship between the derivative of g and the function f? Ooh, yeah, I mean, that's pretty good close. That's pretty close. So let's go back to our definition of a derivative, right? Our definition of a derivative is going to be g of x plus h minus g of x, the limit as h goes to 0, of g of x plus h minus g of x all over h. Everybody agree with that? Let's look at what this is. G of x plus h minus g of x. So here's x plus h. So g of x plus h would be that area. Everybody agree with that? Here's x, so g of x would be this area. Everybody agree with that? So g of x minus, or g of x plus h minus g of x would be that area then. Let me use a different color or something. Right? Everybody's okay there? Okay. So we can approximate that area because this is a rectangle. The width of that rectangle is h. And the height of that rectangle is going to be f of x. Everybody's okay with that? So I take this. Well, let's just do it up here. And there I notice what's going to happen with my h's. They cancel out, which is wonderful. Is there any h involved in f of x? No. So we can treat it like a constant. The limit of a constant is just the constant. The derivative of g is just the function inside of the integral. The derivative of g is the function left inside the integral. So what are we saying then? We're saying that like d dx of the integral from 0 to x f of t dt is just f of x. What's going on here? The integral is being canceled out by the derivative. That's the takeaway, that these two are inverse operations. And likewise, what's going to happen with the integral with respect to the derivative? The integral is going to cancel out the derivative. Exactly right. They work just like inverse functions, like cosine and cosine inverse, or exponent base and log, or squaring and square root. They work just like that. Inverse operations of each other. Yes. So we formalize that as the fundamental theorem of calculus part 1. Now this works. We do have some limits on when this is going to work. So my function that I'm taking the integral of has to be continuous on the interval we're taking the derivative or integrating on. But provided we have that, then that function g is also continuous on the interval and differentiable on the interval, where the derivative of g is just f. And this is what I just showed you a moment ago, right? Is that using kind of the more common Leibniz notation, that the derivative is just canceling out the integral. Okay. And I mentioned this, provided what? We had it up here. Okay. So, example, we have the function g of x equals the integral from 0 to x of the square root of 1 plus t squared dt. And we want the derivative. Notice how big I'm writing this, because we're going to do it in one step. What's this derivative? The function that's inside the integral, or the variable is x. That's it. Right? The derivative is just canceling out the integral. All we're left with is the function inside, but it needs to be with respect to x instead of respect to t. So the variable just changes the match. But that's it. Well, I got rid of the integral, and I got rid of the dt. Yeah, when I took the derivative, those things just kind of cancel out. And then my variable needs to change to match. But that's all that's happened. That's what the fundamental theorem of calculus part 1 is giving us. Will they always be that easy? Not quite. Let's take a look at example 4 here. The difference here is that we have this x to the 4th here. I know that's kind of hard to read. It didn't copy in very well. So we know that g of x would be this, right? So what's g of x, or how do I get an x to the fourth there? Well, I do a function composition, right? If g of x is the integral from 0 to x of, oh, I'm sorry, should be a 1 there. Secant t dt, then g of x to the fourth should be the integral from 1 to x to the fourth secant t dt. Everybody's good with that? So if I want then the derivative of g of x to the fourth, what do I need to use to take that derivative? If I have the derivative of a composition of two functions, what tool do I need to do that? Chain rule. Very good. So the chain rule is going to be give us the derivative of g, which is just secant with the inside plugged in, times the derivative of the inside, which is the derivative of x to the fourth, which is 3x cubed, or I'm sorry, 4x cubed. And we're done. So again, examine what happened here. To do this derivative, all I did was I took the upper bound and that got plugged in, and then I had to multiply by the derivative of that upper bound. Elvis?
So the 1 doesn't matter?
Not a bit. Because the fundamental theorem of calculus gives the lower bound as an a. So whatever it is. We don't care. As long as it's a constant. Is that okay with you guys? Well, you probably wouldn't see that in a course like this. But what I would suspect that you need to do is to break the integral like we've done before. So I'll go like a to some constant and then some constant to my b. And then use my integral rules to make it negative and flip the bounds. And then I can fundamental theorem of calculus each one separately. That's a guess as to what I would do there. All right. Everybody still doing okay? This is the big payoff. Part 2. So it says if f is a continuous function on that closed interval from a to b, then the definite integral from a to b of f of x dx is cap f of b minus cap f of a, where f is any antiderivative of f. Hold on a second. What is this now saying? That I can do the definite integral by just using antiderivatives. No more limits, no more sums, no more summation formulas, all of it gone. All we need are the antiderivatives. So let's look at here the integral from 1 to 3 of e to the x dx. Notice how little space I left to do this. It's because that's all the space I need. What's the antiderivative of e to the x? E to the x. And then I'll just evaluate that from 1 to 3. So I'll do e to the third minus e to the first. Done.
What's the notation of the right dx?
That's just, we usually use like, some people write it this way with a bracket around it. Some people just put a vertical bar. That just means that we're going to evaluate at those 2 points and take the difference. Notice that we did this problem already. This was a 5-2 example. Let's go back and just show you what that took to do that. Right, we did that somewhere. Here it is. So go back to 5-2. This is what it took to do that same problem. Remember doing that? What a nightmare that was? Compare that to what we just did. Whoa! That is a life changer right there. Right? How much easier does that make our life? Let's do another couple. This example says we want the area under the curve for the parabola y equals x squared from 0 to 1. So I know that area is the integral from 0 to 1 of x squared dx. What's the antiderivative of x squared? X cubed over 3. So I have 1 cubed over 3 minus 0 cubed over 3, which is just 1/3. Notice this was a problem that we had done before, I think also in 5-2. Let's go back and look real quick. Where did we do this? Maybe it was a 5-1 problem. Oh yeah, I think it was the last thing we did in 5-1. We did it somewhere in 5-1. Where did you go? This is it. Look at that. Took all that junk to get down to that same 1/3. How much space did it just take us? It's like 2 equal signs or something, right? Guys, this is what I'm talking about. All right. The integral from 3 to 6 of dx over x. The better way to think about this would be the integral from 3 to 6 of 1 over x dx. What's the antiderivative of 1 over x? Close. Yeah, the natural log of the absolute value of x. Again, we wouldn't have been dinged on this one since both values of x were positive. But technically speaking, yeah. And what's the, I notice here, I can do something with this, right? That's the quotient property of logarithms. So I could simplify this a little bit more to just make it the natural log of 2. But this is what I'm talking about here. How much easier is doing an antiderivative than all that limits of sums of nonsense? Significantly easier. What's up? So the dx is like the delta x in my previous calculation, where it just kind of is along for the ride. So when I do the integral and write it as the antiderivative, it goes away with the integral symbol. So once the integral symbol is gone, once I do that integration, The dx is gone too. Is that okay? All right. Last one, or last example, then we're done, Zos. Sound good? Find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. So that's just integrating from 0 to pi over 2 of cosine x dx. What's the antiderivative of cosine? Sine. So that's going to be sine of pi over 2 minus sine of 0. What's sine of pi over 2? 1. What's sine of 0? 0. So that's just 1. This is nice. Right? How much easier does this make life? Now, not all integrations or not all antiderivatives are going to be as easy to compute as these ones are. Notice on each of these, this was like all we're doing is running in reverse a single derivative rule. What happens if the derivative that we're, or what if the antiderivative we're needing to do is the result of a product rule, or a chain rule, or a quotient rule? It could get a little bit trickier, and we'll develop the tricks on how to deal with some of those situations throughout the rest of the chapter, or throughout the rest of the semester. Specifically, though, in section 5.5, we're going to look at the chain rule in reverse. The other ones are a little bit, I don't remember if those are A, B, or BC topic only. I'd have to double check. I intend to think it's going to be BC topic, not an AB topic. But we'll do it if we have time at the end, because I think it's a good one to see. So, again, in summary, Fundamental Theorem of Calculus, parts 1 and 2. Part 1, derivatives and integrals cancel each other out. Part 2, to do integration, a definite integral, I can really just do an antiderivative and evaluate at the bounds. That's it. That's the gist of Fundamental Theorem of Calculus, parts 1 and 2. Massive helpful, right? We've directly connected these two branches of calculus. Integration is really just the antiderivative. Integrals and derivatives cancel each other out. Yes. We've got a lot of time left. You guys want to do a couple of the homework problems together? Of course. Oh, can I ask you guys, this is a question that we didn't really address when it came up. So let's say, for example, right here, we said that the antiderivative of cosine was sine. When we did section, 410, that wouldn't have been correct, right? What did we have to also include? Plus c. Why don't I need to include a plus c here? Any antiderivative. What antiderivative are we picking? The one where c is 0. So just figured we should mention that. There are indefinite integrals, but it doesn't get harder. No, you just put a plus c at the end. That's all. Yeah, it's the same thing. You're doing math TikToks. I love it. All right. Let me just grab a couple of these problems. We'll do a couple problems together from... You guys make me so proud sometimes. Oops.
Yeah, I thought you like the best. Yeah. I know, you might have been able to like scroll something else.
All right. So 11, 15, 17, you want to do one of these together? Sure, I can wait lots of seconds. While we're waiting, why don't you just take a look at those three and see if one of those like tickles your fancy. Anybody got a preference there? Sure, we can do 17. Says use part 1 of the fundamental theorem of calculus to find the derivative of the function. Okay. We have one problem that we need to take care of before we get started. What problem is there with the way this integral is written? Yeah, the lower bound is where the variable is. So what do I need to do? Yep. I can, if I make the integral negative, I can flip the upper bound and lower bound. Cool with that? Do this. Okay. So the derivative of g of x is going to be going to be the function with that plugged in times the derivative of that. Oops, and I forgot my negative sign. So if I simplify that down, I just get, what do I get? 3 and I wouldn't simplify past that. That looks good to me.
Just the derivative of that little.
So, right, when doing the derivative of g, that's just going to be my, because I already have the integral sign out front, it's just going to be the f with whatever that bound is plugged in times the derivative of the bound. That's it. This derivative. The derivative of that is -3. So the negatives canceled out. And then I just stuck the 3 there. Because they had to go somewhere. Numerator out front of the whole fraction, either would be okay. Or times at the end, whatever, you know. What do you guys think on that? It's not bad, right? Let's do one of these part 2 problems, maybe. Okay, what do we got here? 19, 23, 25, 27, 29, 35, 40, 41. Any of those feel like doing? 41 you want to do? Is that what you said? Okay. It's u plus 1. It's the integral from -1 to 1, e to the u plus 1 du. And here we're using the Fundamental Theorem of Calculus Part 2. So what's the antiderivative of e to the u plus 1? Well, that would be the derivative of that. But what is the derivative of e to the u plus 1 times 1? Or what is that? I'm sorry. The derivative of e to the u plus 1 is just e to the u plus 1. So what's the antiderivative going to be? E to the u plus 1. That's right. So if we evaluate that from -1 to 1, we have e to the 1 plus 1 minus e to the -1 plus 1, or e squared minus 1. This is awesome, right? I should also mention to you guys that all these definite integrals you can also check on your calculator. So if I wanted to check this one, I could go to my y1 and type in e to the x plus 1. And then if I press the math button and I scroll down to the bottom and find the fn int, that's function integration,
Where do you go?
math, and then down to the bottom. Yeah, that sounds right. Depends on your operating system, whether it's 9 or A or whatever. So now just fill this in. It's the integral from -1 to 1. I put my function into y1, and my variable is x, so I'll put an x for the dx, and then press enter. And if you notice that this is the same thing as e squared minus 1, so you have a checker for any definite integral.
Oh, for 19 through like 44, how did you know what was part 2?
Because we're asking to evaluate the definite integral. It didn't ask us to find the derivative of an integral like it did on the previous ones.
Okay, so the first part was derivative.
Mm-hmm.
The other one,
There's no more. Oh.
How would you do 35 since that's going to be
35?
yeah.
Ah, I wouldn't do it as a quotient rule. So 35, that's exactly what I'm going to do. Is I'm going to think about this as that and what's the antiderivative of v to the negative 1? Or 1 over v? And then the natural log, right? And then the integral of 3v squared. Or I'm sorry, the antiderivative of v squared is v to the n plus 1 over n plus 1. So I have natural log of 2 plus 2 squared, or I'm sorry, cubed, minus the natural log of 1 plus 1 cubed. So that's natural log of 2 plus 8 minus the natural log of 1 is 0. So this is just natural log of 2 plus 7. Does that feel okay? So again, the trick was breaking it apart. These are the same kind of tricks I tried to get you to do when we did the derivatives, because this is the place where if you don't do it this way, there's not a good antiderivative to do it, right? So like the algebra rearranging becomes like a critical skill here, and seeing that like, hey, can't I just like write that as two separate fractions and then reduce everything down to get rid of, so it just becomes like polynomial things. Yes, is what the answer is there. That's exactly what you want to do. And again, if you wanted to, you could check this. Oops, that's a third. So we'll do function fn, or math fn int 1 to 2 y1 dx, and this should be the natural log of 2 plus 7. Yup. So this homework, although there's kind of a lot of problems, is a pretty easy homework assignment. Way easier than 5.2 was. 5.2 was a pain.
I did like 4 problems and it took like 30 minutes.
It's a pain. It's a pain. Here's the good news, though. Do you suppose I'm going to ask you to do, like, evaluate a definite integral using, like, the techniques you did in 5.2?
On a test?
On a test? No way. I wouldn't ask you to do that.
I thought you said we were going to have to do all that stuff on a test.
I mean, there's stuff from there that you have to do on the test.
Wait, you said 5.1 and 5.2 we're not gonna do.
Like he just said we do that.
Oh, we do?
Oh, I heard no.
Check.
When you flip the integral and make it negative, do you distribute that negative through the function?
Yes. So that negative sign would be distributed through all the terms in the function. Yes. 100%.
Regular decisions are 5 weeks. It's been 5 weeks of this. It's like it could be really, but it's still fat.
Sure.
Don't start working out next
Oh.
month.